Welcome to this screencast on Big O notation for ICS 211. So why or how can we compare 2 or 3 or 4 different implementations of the same algorithm or program? Because we're talking about abstract data types, we're really talking about the operations on it, but the implementation we don't care about, but we want to be able to compare and choose the best implementation of that particular algorithm or data type for our application that we're running. So what are some of the ways that we can compare different implementations? Well, one of them is to consider the size, the memory size of that particular implementation. Does it use lots of data or lots of memory when it runs? Do we have to, is it wasting space and all these kinds of things? Well, with modern computers and RAM being so cheap, the size really isn't that important anymore. You can always go buy more RAM. So how about time? Well, time's a better way of measuring because we don't have a lot of time, and time is expensive. We don't want to be wasting our time waiting for the implementation to finish if it could be done quicker. And in fact, for certain problems, they won't complete before the heat death of the universe. So we want to consider time or runtime as the thing to compare different implementations. So I want to get an implementation that has a smaller runtime than one that has a long runtime. So how do I measure time? I could get my program or my algorithm, start with stopwatch, run the program, and then when it's finished, stop the stopwatch and know how many seconds it took. Well, that's not a great way, because what happens when the program it doesn't just run. It's got to start up the JVM, it's got to load the classes, it's got to do all this extra work before it actually really starts my program. And some programs might take weeks to complete, and so I don't want to sit here waiting for a week. So using a stopwatch just isn't the right way to go. So how else can we do it? Well, we use code analysis or runtime analysis to figure out, by looking at the code, how long we estimate it will take. And this takes out the thing of, is my laptop or my computer a supercomputer, or do I have an old cruddy TRS-80 machine from the early 80s? So code analysis, you can not worry about what CPU or how much memory you're using. You can actually take a look at the code to get an estimate of its runtime performance. So how do we do runtime performance? Here's a simple example of a very simple method that basically has a bunch of statements. There are no loops, there's no if statements, so we can basically say each of these statements will take some amount of time. Some take a different amount of time. This assignment may take longer than this assignment. This assignment's probably the same C2. The multiplication and assignment's going to be different than just the assignment, and then an increment is going to take a different amount of time. So we can just give it these notional constant time measures. So what's the total amount of time for this method? Well, it's C1 plus 2C2 plus C3 plus C4, which basically, if you boil it down to a function, it's constant. You add them all up, it's a constant number, and it doesn't matter upon the size of anything, the value of amount doesn't matter. It's going to take a constant amount of time, that many instructions added together. So now let's add a little bit of a difference to the code. We added a while loop, and so again we take a look at how long things are going to take. But in this case, notice that the while, this comparison of I less than n, is going to take some time, and it's going to happen n times, or n minus 1, but basically n times. And so the multiplication will occur n times, and the increment of I will occur n times. So we have some things that only occur once, and then we have some things that occur n times, and something that occurs n. So the total amount of time is, again, these constant times plus that, and then we have the inside the loop where that's, C3, C4, C5 occur n times. So what is that reduced to? It's a constant T1, which is these summed together, times n, plus another constant. So basically, as n grows, this time is going to be more a factor of n. So if n is 10 billion and ct, this constant is 3, well, this is a much bigger number. In fact, if this number is 10 billion, it actually starts to outweigh the constant that's multiplied for it, because you can say, oh, it's 100 billion or 200 billion, and so those numbers will be much larger than any multiplier in front of them as we get further out as to larger n's and continue on. So let's modify the code a little bit more. We added a second loop inside the outer loop, and again, so now we say this has got your constant time. We start getting constant time n's times n, but then these inner ones, we have n for the outer loop, and then we have n for the inner loop, because basically I goes from 1 to n, so that's why we use the n. And again, these are on the inside, so what's the total time? More complicated. We have constant time things, we have some things that run n times, and then we have some constant time that runs n squared. So again, as a function of n, we say we have a constant term that we can ignore. When n is large, this just falls apart, we don't really care. Again, when this term we can even start ignoring when n is large, because this thing is going to be so much smaller than the n squared, so the n squared term is going to dominate. So this basically becomes an n squared function, or the time it takes for this method to run is in order, big O, order of n squared. So what are we talking about? We are saying the time it takes to run your thing will be less than some function for values greater than k. So if n is greater than k, then the time it takes for your program to run will be less than some function, some limiting function of time, and that's the big O. So again, we just simplify. If it is a constant time, we're going to say big O of 1, which means it takes constant time. If it's n plus a constant, then it's a big O of n. If it's n squared, again, if n gets large enough, these terms are too small to worry about, so we only think about, we call that big O of n squared. So that's a way of comparing the algorithms. And so what are some of the different big O's that are around? Like I was saying, big O of 1 means constant time. That does not mean 1 second, it just means the algorithm or the function or the application that you're analyzing takes a constant amount of time independent of how big the data input is, how big n is, how many things are in the array, how many things you're searching, it's a constant time thing. If you divide the problem by a third or a half or something, that's what we call, and you keep doing that, so you're always working on half and then half and half and half and half, that's called log n, so that as n gets larger, it still grows, but it grows much more slowly than, for example, the square root of n. Some problems can be solved using things that take the square root of n, or even linear time, where as the size of the thing, of the problem, the number of items or whatever, gets larger, the time it takes grows in a linear fashion. In a little worst case, you have n squared, so like our double loop one, as n gets larger, the amount of time is growing in a quadratic form, n squared, or even worse, n cubed, so it's going to grow quicker than n squared. And then one of the worst around is n raised to the n, or 2 raised to the n, and then n raised to the n, whereas this, as the size grows, the time it takes to execute that algorithm or program takes a great amount of time. You do not want to run big O of n to the n or big O to the n algorithms or programs unless you know your size is going to stay small. So we can now take a look at the programs or different implementations and make a decision on which one we would prefer to use for large n's. Again, when we're down here in the small n's, you can get some very strange behavior. For example, for small n's, maybe you do want the n to the n because it is going to be less than, for example, a big O of n or even constant time. But in general, you want to choose the algorithms or programs that have these better performing big O's. Thank you for your time.